Hi, everybody. Thanks for coming to my talk entitled Productionizing Machine Learning at Scale with Kubernetes. I wrote this talk in mind for the practitioner who could potentially be designing his or her own system in Kubernetes, and maybe asking questions like, are there enough open source tools available in the Kubernetes ecosystem for building out our own platform? Is it too difficult to use for data scientists who may not have so much experience with Kubernetes and Docker? I think the answer to both of those questions is that it's not too difficult. And in fact, if you have the right type of data scientist at your organization, namely a full stack data scientist, the flexibility that Kubernetes gives you is actually preferable. And there are a number of open source tools that have been developed over the past few years to give you things like model deployment and model monitoring for free. So before I dive into the details of the talk, I want to talk a little bit about my company, TWiML, because it may be relatively unknown amongst many people, actually. So what TWiML does is partner with the world's leading universities to create the world's best online education. What this means in practice is that we act as brand stewards where we partner with universities and create things like short courses, boot camps, and online master's programs. For example, we partner with schools like USC, UNC, Yale, Harvard, NYU, Fordham, and create online accredited master's programs that have both synchronous and asynchronous content. So as a student, you would log in from anywhere in the world, and you'd have a real course, a real class with other classmates and professors teaching you the material. So what does TWiML do specifically? So we offer technology and a host of services to let essentially the universities just do what they're best at, which is render admissions decisions and teach content, right? So what does that mean for TWiML? Well, we do things like digital marketing, we provide the technology, and we provide a host of other services. So what are some of these services? Well, if you're a school that needs placement in the field, for example, it's a nursing program or a teaching program or a midwifery program, we actually place you in facilities near your own home. So a nursing student who lives in Pennsylvania but is attending a program in California will actually be placed in a hospital or facility near his or her home in Pennsylvania. So that's just one of the services we provide. I'm going to speak mostly about the online master's degree part of our business because that's what I focus on specifically. So what does data science do at TWiML? Well, we're responsible for optimizing basically any and all parts of the business. So we partner with different teams within the company, teams like marketing, finance, sales operations, and we provide data and decision support tools to help them do their jobs better. So what are some of the use cases that we work on? Well, we do data-driven program selection, right? So when we decide which programs we want to partner with, we actually have machine learning models that select which of these programs we should go after. We do enrollment forecasting, we do student churn analysis. So when a student is enrolled in one of our programs, we want to be able to identify students who are at risk of potentially dropping out. So what can we do with that information? Well, we can reach out to them. We have admissions counselors and student support specialists who basically maintain one-on-one relationships with a student over the course of his or her lifetime. And this person may reach out and ask if things are going on or if they need additional resources that potentially they can use to keep them in the programs longer. Other sorts of applications include like applications of NLP to analyze surveys. We collect a lot of text data from our students, our faculty members that tell us about how the programs are going, and we use those insights to improve our technology, our services, and these sorts of things. So as the director of data science, I focus specifically on the pre-enrollment part of the process. So when a prospective student visits one of our websites through some marketing channel, to when they start filling out an application, to when they're admitted and choose whether or not to register, I run the machine learning team that is responsible for optimizing that entire journey, right? So that includes things like paid marketing optimization, enrollment forecasting, as well as prioritizing prospective students who may be at risk of not continuing on through the application process and determining what steps we can, how we can intervene to help them out. So when I joined TWiML about 2 years ago, a little bit over 2 years ago now, my responsibility there was to essentially scale up the machine learning that was already in use. So the data science team was in a particularly interesting place. They had already had a bunch of models in production, right? And several of these had actually become mission critical. So we were past the POC stage, and we were building out things that were already being widely used across the company. The true issue was, though, that the infrastructure that existed was actually quite immature. The data science team at the time consisted mostly of people who were strong on the stats side, but were a lot, didn't have as much engineering experience. And most notably amongst this was all of the production workloads were running on a single EC2 instance. Right, so for someone who's coming from an engineering background, this was pretty frightening. And I actually went through, and this thing was called the R server. So I went through our Slack archives at one point in time and just looked at all of the examples where the R server had gone down for some issue. And I copied and pasted these things and made this little graphic on the side here. And I presented this in a talk to my teammates called "Please Stop Using the R Server, Please." And I thought, it would be good up here. So, if we wanted to scale up our work to, to new heights, it wasn't going to be possible to stay on top of this workload. So let me talk a bit about the machine learning models themselves, because I think it'll be helpful to understand why scale was even important. So if you're a nursing student, your requirements, your motivations, your previous courses are going to be quite different from those of a business student, right? So we have nursing programs and we have business programs. So the data generating processes for each of these are quite different from one another. But it doesn't just stop there. So if you're a business student at one school, say UNC, you're also going to be quite different from a business student at another school, say American University, which are both partners of ours. So when we train our models, think of student churn as one of the examples. We actually train our models at the program-specific granularity to capture all the nuances of the different data generating processes, right? So when we do any of our projects, training one model doesn't really mean training one model. It means training one model per program or per university partner. And we have, over 70 university partners, which most of them have multiple programs with us. So operationally speaking, there's a question of scale there. Not only that, but we also have historical snapshots of all of our data, because a lot of these are sort of time series type questions. So we train multiple models per different points in time. We've automated our model retraining. So what this really amounts to is we have a lot of models that we build and train regularly and deploy regularly. So we need a system that can support this huge number of models. And another beneficial part of this is that many of these models are sort of completely independent from one another, right? So the model building process for UNC doesn't affect the model building process for American University. These things don't need to live on the same machine. So it's pretty trivial to parallelize over this operational structure. So what were the goals? Well, we have a small team. We're about 5 data scientists. The data science team in general is about 30 people, but that includes a lot of business intelligence folks. And we have a couple of engineers. So we couldn't really set out on a mission to build an entire platform like Uber's Michelangelo, or if you were here yesterday, the Capital One team gave a good talk on how they used Kubernetes. So we needed something that would enable us to get off the EC2 instance, right? That would parallelize our workflows and enable us to run something like around 1,000 model training and inference processes per day. But we knew that we didn't want to invest in a large platform building process. So essentially we decided that we were going to buy a platform, but that procurement process was going to take a pretty significant amount of time. So we needed something quickly. And the rest of the organization was already adopting Kubernetes, and I had built a Kubernetes-based system at my previous job. So I thought okay, let's build something out in the interim with Kubernetes. This has sort of become the de facto system we use today. So it was pretty amazing for me to think that what started out as sort of an experiment has become a production system. But there's a lot of lessons that we learned along the way, and I want to share those with you, as well as how exactly it is that we use Kubernetes. Oh, and finally, the last constraint was I didn't want any of the data scientists to hate their lives when they were using the system. If it was too complex or just too opaque, it would be more frustrating than anything else. So The way we really use Kubernetes is there's two main use cases what I like to think of. There's the R&D use case, which is a data scientist prototypes new models, builds new models, has new techniques, and then there's the production workloads, which is model retraining, model deployment, obviously online inference. So I've broken these down into two separate slides, and we can touch on R&D first. So there's two major paradigms here. One is browser-based interactive programming environments, things like Jupyter, things like RStudio. We're a big R shop at 2U, so you'll see R a lot. That's why it was called R Server. And how do we build this thing out? Well, essentially we deploy these things as Kubernetes deployments, right? And the deployments create replica sets, which deploy pods. And pods are like the atomic unit of work in Kubernetes. The replica sets ensure that if a pod dies for whatever reason, it'll be restarted. And the pod is actually the thing that is running Jupyter or RStudio. On the other side, we have load balancers that actually take incoming requests from people who are using the services, and there are ingresses, so you can actually access these things through the browser, right? So this is a very typical microservice pattern in Kubernetes. There's nothing very nothing very crazy here. If you're building out microservices in Kubernetes, this is very typical, and that was one of the benefits of this approach, is that we can use something that was well tested in production. So if you're using a notebook and you're running these experiments, this is fantastic and great as a developer. But the real benefit of our adoption of Kubernetes was the fact that we can run large-scale experiments over the entire cluster. So as I mentioned, if we're training a student churn model, we're really training this for multiple universities. And on top of this is that we're training it for all of the previous cohorts. So this is sort of like a backfilling approach. So we want to see if the model performed well last year, half a year ago, or currently, right? So the benefit, how we do that is essentially we deploy a single Kubernetes job, which then spawns many other jobs. Right, so you can think of that job and the root node there as sort of the entry point to the experiment. And what that job is responsible for is essentially looping over either a set of degree programs or a set of feature sets, and spawning a new job, which then runs the actual experiment for that given school in one single in a single pod. Right, so that's the main architecture there. Right, so if you're running a large hyperparameter sweep for each degree program, you're able to do that with this pattern. So the benefits of these two patterns is that we can actually really reuse them for our production workload, right? So this is what our production workload looks like, and it's essentially very similar to our research and development workload. So on the left-hand side, we have online inference, right? And online inference looks exactly the same as serving notebooks or serving interactive programming environments. The only difference is that instead of serving the actual Jupyter Notebook or RStudio instance, what instead we're serving are the REST APIs that have our predictions, right? So these REST APIs accept incoming requests with some data, generate the prediction, and then return these to the user or service that initiated the request. And typically our REST APIs are just written as small-scale Flask applications or Plumber applications if you're using R. I didn't know this was the icon for Plumber. I think it's hilarious. So right, the only thing that's different for online inference is that rather than serving the application, we're serving the REST API, right? And what this enables us to do on the infrastructure side is reuse a lot of our code, right? So our code for IDEs looks almost the same as our code for online inference, except for the application part of the application code, the application logic. On the batch training and inference side, this looks exactly like our experiments, right? The only difference is that rather than have a job as the entry point to the experiment, we have a cron job as the entry point to our experiment, right? And what our cron job does is just run a job on some schedule, right? So we run batch inference each night for a set of models. So now we just schedule one cron job to kick off each of these batch inference jobs each night. batch inference is one of the big things we do each night. Another thing is model retraining, right? So we retrain many of our models, let's say weekly. So now we just schedule a Kubernetes cron job to retrain our models on 1 day a week, and that's how we've essentially automated model retraining. We have a bunch of internal libraries that we've written to take the model artifacts and the retrained models and automatically deploy these, right? So, and I'll get into this a bit later, we already had a lot of libraries to do a lot of these production use cases. So rather than reinvent the wheel and use some of the Kubernetes tools, we just adapted the tools we had already built to our Kubernetes system. So what were the results of this system, right? Well, what did it enable us to do? Did we achieve our goals, or did we, spend a lot of time developing a Kubernetes system without improving our models? Which, at the end of the day, is what we really wanted to do, right? We wanted to. The differentiating value for us as a data science team is not the infrastructure, but the models that we're building and the insights that we're generating. So, there were things that both went well and things that didn't go so well. And I think this is what I consider to be really the meat of the presentation, and what I want developers and data scientists and machine learning engineers to take away are the results that we achieved and what we learned. So the things that went well are we were able to run really large-scale experiments, right? So just in the first week alone, we were already training like tens of thousands of models, running tens of thousands of batch training and inference processes. And this was largely driven by our ability to parallelize all of our experiments. So as I mentioned earlier, we train models for different programs. This was trivial to parallelize over Kubernetes, right? And this was essentially the main goal, and it was quite easy to achieve. On the development side, most of the data scientists, I would say, didn't have much experience with Docker. So what really worked well for us was coming up with a bunch of shared Docker images that had many libraries pre-installed on them, right? So obviously there are the open source libraries that you can pre-install, but we have 5 to 10 internal libraries that we also pre-installed on these Docker images and made available. So if somebody wanted to get started using RStudio or deploying some online inference algorithm, they would just use these Docker images that we created as their base images, and wouldn't have to do any work on iterating on the Docker images, which was really valuable. So I would highly recommend that if you're starting to use Kubernetes or starting to use Docker for your team, come up with some base images that you can share and use. That'll just greatly simplify the workloads. Next was how we actually handled the creation of the Kubernetes objects. Excuse me. So we didn't really have an API. That would be something that we would develop if we continue to invest in the system. Instead, we just started with something very simple, which was a set of makefiles that had common workflows and common patterns in them. So, for example, one of these commands might be to create an experiment, right? So the make experiment command would just build a Docker image, package up the code into the already existing Docker images that I just previously described, tag the image, push the image to some repository, and then create the actual corresponding Kubernetes object, right? So those are all steps that if you have to figure out yourself as a developer and you're not familiar with Kubernetes, can take days. But they're really just like 3 or 4 lines of code. We offer this make file to whoever wanted to use it, and that just greatly simplified the experience, right? So the common pattern that's going to come up again and again with the results is make things as simple as possible, while maintaining the flexibility you get by just using vanilla Kubernetes. So what didn't go so well? So I mentioned that one of the big reasons for us using Kubernetes was to parallelize our workloads and run larger experiments. What we didn't have in our cluster, which is managed by the SRE team, is auto-scaling enabled, right? So what this amounted to was, we were very excited the first week, and we started running larger experiments than we had ever been able to run before. And already within the first week, we would just clog up the cluster, right? We wouldn't have it. We would use up all of the compute, and we'd use up the entire quota. So what did we do? Well, we went to SRE and we said, hey, can we have more nodes on the cluster? They said, sure, it's going to cost you $20,000 more a year. I said, okay. And then the next week, we clogged all of those up. All right, so obviously that's not going to work very well. So instead, if there is something that I would go back and change, it would be the lack of autoscaling and making sure that we could have autoscaling enabled. There are a couple of tools out there that you can use to do this. One was open sourced by OpenAI a couple of years ago. Essentially, what that does is just poll the cluster for the nodes available, and then reach out to your cloud provider like AWS and create nodes if are needed, and then it'll automatically scale it back down once the jobs are complete. Right. So another thing was pod cleanup. So when we run these large-scale experiments, sometimes there's 5,000, 6,000 jobs being created at one time. When these jobs complete, the nodes, the underlying nodes are freed up again, but what they leave some cruft behind in the form of metadata. And you need to manually clean this up. So, we would run some jobs, maybe have 10,000, 15,000 jobs left over, but the metadata would remain behind. And what this led to was the actual Kubernetes API becoming very, very slow. So if we want to pull the API and see the pods, see some metadata from the pods, the API got much slower. So how do we get around this? Well, we created some jobs to actually go in and clean up the system. So we delete some previously run jobs, delete some previously run pods. And this is where naming became quite important, right? So if you're running experiments in different projects, the naming conventions you use for these are quite important. You want to add things like the date in which you run the experiment, in our case, the university for which we were running the experiment, the type of model we were running, because what this allowed us to do for the cleanup part is be able to filter on the previously run jobs and delete only the ones that we wanted to delete, right? So naming is one of the most important yet hardest thing to do in programming, and that extends to this case definitely. Next there was also a lot of configuration files that were in our project repositories. I mentioned we didn't have a centralized API or a library that we used to call to create all the Kubernetes objects. Instead, we had one single repo that had templates that data scientists could use. They would go to this repo, they say, okay, I want to run a large-scale experiment, or I want to deploy some online inference. These are some previous Kubernetes templates that were used to do that. Let me just let me just copy those into my repository, make whatever edits I need to, and then I can just use the system and the make files that way. What this led to, especially for the less experienced Kubernetes users, was a lot of cruft being left over in their repos. So they might have several different iterations of a kube config to run an experiment, and this was if you were them, this was no problem because you knew what you were doing. But if you were any other data scientist and you were joining this project and you had to figure out which actual file to use, this became quite complicated, right? So the letting data scientists write their own kube config files was great in terms of flexibility, but made it operationally more difficult if you wanted people to join the project and start adding on. And finally, and obviously, I think there's a long ramp-up time for people who don't have experience with Kubernetes. And who don't have experience with Docker especially. There's just a lot of moving pieces for you to learn, but this is not to say that you shouldn't do it. And if you have the right people, as I'll mention a little bit later, it's actually, I think it's a beneficial thing to do. So what would I have done differently, right? If I can go back in time and actually change what I did, what would those things be? And this is, I think, good learning for people considering doing this. Well, for the batch jobs, I would definitely go back and just use a job scheduler, right? We deployed these things as batch jobs, and I think it was a bit more complicated than it needed to be. What I would do today is install something like Airflow and use Kubernetes operators to still get the benefits of running the jobs over Kubernetes, but I would have a UI, I would have monitoring, I would have retries for free, and that would definitely be the thing to do. We do a lot of batch, so that would definitely be a thing I would go back and change. I would also set up single-click initialization for our IDEs. Right, it would just make things simpler. Obviously, we can always use better documentation for common workflows. And then I would automate more of the Kubernetes object creation, right? So we made it as flexible as possible by allowing users to edit the templates. But there are now tools out there that give you flexibility, but also allow you to automate some of the creation of the object. So one of these tools is called Flotilla. I believe it's by Stitch Fix. Basically, all you have to do is specify the Docker image and the command you want to run, and as long as you've set it up correctly, it'll do the work over Kubernetes for you. So these are things I would do differently, but what would I continue to develop if we kept iterating on this system? I think this is, there are things we would change because, they sucked or they didn't work as well, and then there are things that were going well and we can continue adding on to. So one thing I would definitely develop is a sort of internal library that would integrate our specific machine learning workflows with Kubernetes. I mentioned the Capital One folks yesterday gave it like an excellent talk. I spoke to one of the guys there yesterday, and I asked him, how many people on your team did you have developing this for? He gave some preposterous numbers. Like we had 30 engineers serving like 1,000 data scientists. So after that, I thought, okay, my talk should be, I can change the title to Capital One system, but like by 2 data scientists for 5 data scientists, right? Like drastically scaled down version of what they built, but their system was awesome. So there's also a blog post that came out a couple of weeks ago by Stripe detailing their system that does this called Railyard. I would want to set up like a single pane of glass view, so you can see like monitoring, logging, alerting in a single place. We had data scientists who had to go between different systems to do these things. And finally, here's a list of services that are open source and exist now. You have Kubeflow and Polyaxon, which are end-to-end. You have Celdon, which does deployment. Istio is a service mesh, gives you like A/B testing. And then there's Argo, which is like a workflow management tool that we're actually integrating right now. So main lessons: make things as easy as possible for data scientists. Right? They'll hate their lives less. Don't reinvent the wheel if you don't need to. Right? We had libraries that did deployment, so we didn't want to use Celdon. Right? There was no reason for us to use Celdon. We already handled deployment. We already have libraries to do feature engineering. Invest in monitoring and logging early on, especially if you're deploying a lot of models. And work iteratively, right? So you don't need to move everything to Kubernetes right away. You can start with your notebook instances, get a feel for that, and then move your online inference over. And finally, if you're a full stack data scientist, what we found is that they actually enjoy learning these things, right? So people always say like, oh, don't give them more things. It's too complicated. And I think that's nonsense. If you have full stack data scientists, they actually enjoy these things. And if you want to learn these things, I've written a series of blog posts that goes much more into depth on each of those patterns I described earlier. You can check them out at my blog. It's called mlinproduction.com. And these are topics I'm very passionate about and write about quite often. So I have a weekly newsletter there for all things like production machine learning, deployment, monitoring, visualization, engineering best practices. So please check out the website. And that's it. Thank you.